PRM Applied Math seminar of this academic year. And we're very happy and thrilled to have Daniel Kuhn from École Polytechnique in Lausanne. And Professor Kuhn received a PhD in economics from University St. Gallen, then did a postdoc in managerial science and electrical engineering at Stanford, then had his first position at the computing department at Imperial College, and since then, since 2013 or 14, I'm not entirely sure, he's a professor at École Polytechnique in Lausanne, where he holds the chair of risk analytics and optimization. His research expertise is in stochastic and robust optimization with a myriad of applications in engineering, machine learning, business analytics, and finance. And I think today's talk will also circle around robust optimization, which is a very current and very interesting topic. So without further ado, Professor Kuhn, please take it away.
Thanks a lot, Tim, for the nice introduction, and thank you very much for inviting me to give this talk. It's a great pleasure. So yeah, we'll talk about mathematical foundations of robust and distribution robust optimization, and these are actually powerful modeling paradigms for dealing with uncertainty and optimization problems. They become increasingly popular because they have many applications of business analytics, data-driven decision-making, and machine learning. And so I would like to propose a systematic and unifying framework to find computationally tractable reformulations for such problems. My talk is based on joint work with Janset Chen from ETH and Wolfram Wiesemann from Imperial College London. So the objective and constraints of an optimization problem are often formulated in terms of extended real-valued functions. And extended real-valued functions are functions that can adopt the value plus infinity. So the set of points above the graph of an extended real-valued function f is called the epigraph of f, and the projection of the epigraph onto the x space is referred to as the domain of f. And throughout this talk, we will focus on proper functions, and an extended real-valued function is proper if its domain is not empty. We will also focus on convex optimization problems whose objective and constraint functions are actually convex, and by that we mean that it's a function is convex if the line segment between any 2 points in the epigraph is also contained completely in the epigraph of f. Okay. So in addition, we'll also focus on closed functions, and by definition, a function is closed if its epigraph f is a closed set, and this means that the limit of any converging sequence of points in the epigraph must also belong to the epigraph itself. So in summary, we will work exclusively with functions that are proper, convex, and closed, and I will abbreviate this as PCC in the rest of the talk. The epigraph of a PCC function is therefore convex, closed, non-empty, and contains no vertical line. Okay, so we will later see that dualizing a convex optimization problem sometimes requires us to transform its objective and constraint functions, and in the following, I would like to recall a few basic transformations that preserve convexity. So first, convexity is preserved under conjugacy, and the conjugate of a convex function f is another convex function f star. To evaluate f star at the point w, we need to solve the maximization problem that is shown here. So here's an example of a convex function. And to construct the conjugate of this function, we can proceed as follows. So for a fixed w, we first construct the tangent of the function f with slope w. And geometrically, the conjugate of f evaluated at w then coincides exactly with the negative intercept of this tangent. So as we increase the slope w of the tangent, the intercept of the tangent traces out the negative conjugate of f, and this is shown in the chart on the right-hand side. So to construct the conjugate, it just remains to flip the resulting graph upside down, and as you can see, convexity is clearly preserved under this transformation. Okay, so second, convexity is also preserved under perspective transformations, and the perspective of a convex function f of x is a function f underline of x and t, where t is a non-negative scalar. Specifically, the perspective of a function f just multiplies the output of f by t and divides the input of f by t. Here's an example of a convex function. To construct its perspective, we first embed f into a vertical plane of a higher dimensional space with a t-axis. And assuming that the original function f resides in the plane corresponding to t equals 1, we can then construct the epigraph of the perspective of f as the cone generated by the epigraph of f. Now, as the cone generated by a convex set is necessarily convex, the perspective function f underline inherits convexity from f. Okay, third, convexity is preserved under infinite convolutions. And to explain this, we first define the Minkowski sum of two convex sets, C1 and C2, as the set of all points of the form x1 plus x2, where x1 belongs to C1 and x2 belongs to C2. So, for example, the Minkowski sum of the disk and the square coincides with the union of all disks whose centers belong to the square. So this could be constructed in this way, for example. And clearly this is convex. So next we define the infinite convolution of two convex functions f1 and f2 through the minimization problem shown here. If you stare at this definition long enough, you will probably convince yourself that the infinite convolution of f1 and f2 is a function whose epigraph coincides with the Minkowski sum of the epigraphs of f1 and f2. For example, if f1 is the absolute value function and f2 is the standard quadratic function as shown here, then their infinite convolution is given by the Huber loss function, which is widely used in statistics. So, and again, clearly the infinite convolution of these two functions then inherits convexity from f1 and f2. Okay, so after settling the preliminaries, let us now focus attention on deterministic convex optimization problems. Now, a convex optimization problem P minimizes a convex function f0 of x over all decisions x that satisfy different inequality constraints captured by convex constraint functions fi of x. In the following, we will assume that all of these functions are PCCs, or proper closed convex, and we will refer to P as our primal problem. Duality theory is a cornerstone of convex optimization and is the workhorse of modern robust and distribution robust optimization. So to construct the dual problem associated with P, we first assign Lagrange multipliers lambda I to the different constraints and construct the problem's Lagrangian function as the sum of the objective function and the constraint functions multiplied with their Lagrange multipliers. Problem P can then be reformulated as an unconstrained optimization problem that minimizes the effective objective function f of x, which is defined as the parametric supremum of the Lagrangian with respect to all non-negative Lagrange multipliers lambda. So the dual problem associated with P is then obtained by interchanging the order of minimization and maximization. And thus the dual problem maximizes the effective dual objective function g of lambda, which is defined as the parametric infimum of the Lagrangian with respect to x. So to express the dual as an explicit convex maximization problem, we can actually go on then and add 0 to the Lagrangian in the form of the term 0 times x. And then we can actually convert the infimum over x to a supremum by just pulling out the factor -1 out of the inner maximization problem. So the resulting inner supremum problem over x is then easily recognized as the Fenfield conjugate, or just the conjugate of the Lagrangian, evaluated at 0. Now recall that the Lagrangian constitutes a weighted sum of convex functions. So from convex analysis, it is well known that the conjugate of a weighted sum of convex functions equals the infinite convolution of the perspectives of the conjugates of the same functions. Okay, so we thus obtained the problem shown here, and note that in this dual problem, in this explicit dual problem, we had to introduce the auxiliary decision variables wi, which are conjugate to the original decision variables x. Okay, so we have thus found a simple representation of the problem dual to P as an explicit convex maximization problem. And from now on, I would like to denote this explicit problem, dual problem, by D. So actually we can prove that the infimum of the primal problem visualized on the left is always larger or equal to the supremum of the dual problem, which is visualized on the right. And this is of course weak duality. We can further prove that the infimum of the primal equals the supremum of the dual if either the primal or the dual problem has a bounded feasible set, or if either the primal or the dual problem admits a Slater point. So this is strong duality. Okay. So having reviewed the duality theory of deterministic convex optimization, we are now ready to address optimization problems affected by uncertainty. Actually, there are good reasons to assume that most optimization problems encountered in practice involve at least some degree of uncertainty. The ubiquity of uncertainty has, for example, already been recognized by the Roman statesman and philosopher Pliny the Elder, who aptly stated that the only certainty is that nothing is certain. So in the following, we thus study decision problems that depend on uncertain parameters Z. Specifically, we assume that the objective function depends on the uncertain parameter Z0, and the ith constraint function depends on the uncertain parameter Zi. So to build up some intuition, it is maybe instructive to first fix a vector Z of uncertainty realizations and to study the scenario problem P of Z, which represents our decision problem for a fixed known uncertainty realization. So we will assume throughout again that the objective and constraint functions are PCC in the decision variable X when the uncertainty realizations Zi are fixed. And this means that the scenario problem is just a normal convex optimization problem, and the corresponding explicit dual scenario problem can be constructed as in the first part of the talk.
Just one quick question, Daniel.
Yes.
So the functions are assumed to be jointly convex in both variables, right? And then when you take conjugates, it's always with respect to both variables.
So in this case, actually, the functions f0 and fi, they're supposed to be convex in X, so that we have a convex decision problem. I didn't say anything about the dependence on the uncertainties, and we will talk about that later, but for the moment, we don't need to make any assumption. We will need later, okay? And the conjugates, they're with respect to X here. So because these are the decision variables, we fix the Z. So you can basically just block out the Z and assume it's not there. It's just the same what we just did before. Yeah, so I denote this by *1. That means it's the conjugate with respect to the first argument here and here, right? So not the nicest notation perhaps, but we couldn't figure out a better one. Okay, so that's what I just wanted to say here, right? That we take the conjugate with respect to the decision variable X. And what this actually means that, the scenario problem is just a normal convex optimization problem, and the corresponding explicit dual scenario problem is exactly constructed in the same way. Oops. Okay, so now let us visualize the primal minimization problem for a fixed scenario Z1 of the uncertain parameters, and we can visualize that by the convex effective objective function. And of course, then the dual problem corresponding to the same scenario is a maximization problem with a concave effective objective function. And under mild regularity conditions, we have strong duality, so the infimum of the primal matches the supremum of the dual. So now let's change the scenario to Z2. Then both the primal and the dual scenario problems change, but their optimal values will still coincide, and the same happens again at the third scenario, and so on. So now if we take the infimum of the primal, if the infimum of the primal equals supremum of the dual for all scenarios, then clearly this equality must persist if we take the supremum over all scenarios in some uncertainty set script Z. Okay. Now let's first take a look at the highest primal optimum on the left-hand side, and let us rewrite the primal scenario problem again as explicitly as a constrained optimization problem. So next, we can interchange the infimum over X and the supremum over Z, and in this way we obtain what we call the so-called primal worst problem. Okay, so note that when interchanging the sup and the inf, we may actually pick up a non-negative duality gap. So the primal worst problem is, of course, nothing else than a robust optimization problem. And here, the decision maker aims to find a decision X that minimizes the worst case objective function, and that is feasible under every realization of the uncertainty Z in the uncertainty set script Z. And this problem can thus be viewed as a game between the decision maker and some evil adversary who wishes to inflict maximum damage. Okay, so let's now return to our identity for the highest optima of the primal and dual scenario problems, and let us focus on the highest dual optimum on the right-hand side. Again, writing down the dual scenario problem explicitly as a constrained maximization problem in this case, and merging the supreme over Z with the supreme over the decision variables W and lambda, we then obtain what we call the dual best problem. So this dual best problem is fundamentally different from the primal worst problem in that the metaphorical evil adversary who selects the uncertainty realizations cooperates now with the decision maker instead of trying to inflict damage. So they're both maximizing. Okay, so the objective function of the primal worst and the objective function of dual best can conveniently be visualized as the pointwise maxima of all the objective functions of the primal and dual scenario problems, respectively. And as the picture suggests, there will be a duality gap in general. However, it turns out that we can achieve gap-free duality under natural convexity conditions. And now we come back to what you asked him. So from now on, we need to make some assumptions about the dependence on the uncertainty. So we will assume that the uncertainty set script set is defined in terms of convex constraint functions, CL, and that the objective and constraint functions are concave in Zi. Actually, to be a bit more precise, we assume that the CL functions are PCC and that the negative objective and constraint functions are PCC in the uncertainty realization Zi for a fixed decision X. Okay, so these are saddle functions then. And these conditions actually imply that the primal worst problem is equivalent to a simple convex optimization problem. So to see this, let us focus on one of the embedded maximization problems over the uncertainty realizations in the ith constraint. And let's convert this maximization problem to a minimization problem by factoring out the -1. Now, using our assumption about the uncertainty set, this minimization problem can be represented more explicitly as a constraint convex minimization problem. And of course, we can dualize this. So this convex problem can be dualized in the usual way. So it can be transformed to an explicit convex maximization problem in the same way as before. And here we should recall that this dual problem involves the conjugates of the objective and constraint functions with respect to the uncertainty realizations Zi. So this is really the conjugate with respect to the second argument here, whereas the first one, the X is kept fixed. Now, as the original constraint function constitutes a saddle function that is convex in X and concave in Zi, one can easily convince oneself that its partial conjugate with respect to Zi is jointly convex in X and the dual variable YIL. So now converting the emerging maximization problem back to a minimization problem by pulling the -1 back into the objective, we then finally obtain the simple convex minimization problem that is shown here. Okay, so actually, all of the evil adversaries embedded maximization problems in the objective and the constraints can be transformed in the same way to an explicit convex minimization problem. So we can substitute them. And once we replace them, we can drop the emerging infimum operators because they all appear on the left-hand side of a less than or equal inequality. And this actually shows that the primal worst problem, so our robust optimization problem, admits the explicit convex reformulation shown here at the bottom. So to show that the optimal values of the two problems coincide, we need an additional, but actually purely technical Slater or boundedness condition. but what's important here is that this convex reformulation of the robust optimization problem PW generalizes and actually unifies many classical reformulation tricks that were developed for more restrictive classes of robust optimization problems. Okay, so I would like to return to the dual best problem, which is the dual of the robust optimization problem that we studied so far. And the conditions on the uncertainty set and the constraint functions also imply that the dual best problem is equivalent to a simple convex optimization problem. To see this, recall first that the dual best problem involves the conjugates of the objective and constraint functions fi with respect to the decision variables x. As fi was assumed to be convex in x and concave in zi, one can again show that its partial conjugate with respect to x is jointly convex in zi and the dual variable wi. And so evaluating the perspective of this convex function only with respect to the first argument wi, unfortunately makes this function non-convex. So the non-convexity of the objective function of this dual best problem is actually also somewhat apparent from our earlier visualization here. So of course the dark red function here is not necessarily concave. Luckily, this non-convexity can be eliminated by a simple variable substitution. So we just need to replace the zi variables with vi over lambda I, where vi denotes a new decision variable that replaces zi. So if we do that, then we convert the partial perspectives in problem db at the top to global perspectives in problem db prime at the bottom, which are known to be convex. So the primal-worst problem therefore admits the convex reformulation shown here. So problem db prime is a convex optimization problem.
Can I ask one technical question? I mean, the case where lambda I is 0 is, I mean, it's a bit swept under the rug, which is fine, but you get the horizon function at 0 or something for the
yes.
But then with the inequality, I don't quite. I mean, playing devil's advocate, I don't buy it. If lambda I is 0, then the inequality will always be satisfied. So how do you preserve the set? Is the question clear? I don't.
Well, the question is what happens when lambda is 0, and actually we spent a great deal of time analyzing that case. Unfortunately, I felt that it's not suitable to discuss this in a talk.
No, of course.
Because actually, so in the paper is all about this. So.
Okay. Right.
And you're right. You get the horizon function, or basically, so the CL function has an epigraph that is a convex set, and the epigraph of the. So if you set lambda to 0, then this perspective will have at lambda equals 0 an epigraph that is just the recession cone of the epigraph of the normal CL function. And yeah, you need to, if you want to prove things, you need to do case distinction, lambda positive, lambda 0, and you need to show that all works out. Actually, the formulas that I show you are correct if you interpret the perspective at lambda equals 0 as the horizon function. So it remains correct.
Of course. That's why I said that I have no problem with that. But then the inequality. So you introduce this lambda or v over lambda I, and in the inequality in the db prime problem, now multiplied by lambda I. But I'm just wondering. I don't doubt it at all. How the inequality will be trivially satisfied if lambda I is 0, right? But no,
it will be trivially satisfied if v is 0 and lambda I is 0. Because this is a positive homogeneous function, right? So it will be 0 at 0, but it may not be non-zero when v is not 0. Actually, this is a type, but this should be vi, as you might guess, right? So
CL is positively homogeneous.
Yeah, no, the perspective, lambda I CL v over lambda I.
Yeah.
When lambda I is 0, this should be interpreted as a positive homogeneous function of v.
Okay.
And it will be 0 when v is 0. It may be 0 when v is non-zero, but generally it's actually not.
You're right. Okay.
So if the CL function grows more than linearly, like if it's a quadratic function, then when lambda is 0, this function is actually a very degenerate function. It will be 0 at 0 and it will be plus infinity everywhere else. But if CL is already a positive homogeneous function, then the lambda I will just cancel out, and the CL will remain this same positive homogeneous function. So yeah, one needs to distinguish these cases.
Okay, cool. Thanks.
Okay, good. Any other questions? Okay, so to summarize, our discussion of robust optimization has shown that the problems we studied are the primal worst and the dual best problems, so PW and DB. And we have found there are convex reformulations PW prime and DB prime. Now, the primal worst involves embedded subproblems, these maximization problems that the evil adversary has to solve, and therefore it seems hard at first sight. It seems to be a difficult problem. The dual best problem has a non-convex objective function, and therefore, of course, it seems also to be hard. Yet both of these problems are equivalent to simple convex programs. And if there are no regularity conditions, the optimal values of these four problems satisfy some weak duality relationships, which are visualized by the blue arrows here. So our convention is that the optimal values decrease along the arrows. If the dual best problem admits a Slater point, however, one can show that all problems are equivalent. And this establishes the so-called primal-worst-equals-dual-best duality scheme, which was first discovered by Damir Beck and Ronnie Benthal. Okay, so that concludes robust optimization. In the next part of the talk, I would like to address distributionally robust optimization. So here, the decision maker aims to minimize the worst case expectation of a disutility function G that depends both on the decision X and the random vector Z. The worst case is evaluated with respect to all probability distributions P of Z that fall within a given ambiguity set script P. So distributionally robust optimization problems can therefore be thought of as zero-sum games between the decision maker and an evil adversary that selects the distribution P. And a distributionally robust optimization problem can thus be viewed as a robust optimization problem where the probability distribution P plays the role of the uncertain parameter. So the most difficult component of a distributionally robust optimization problem is the inner worst case expectation problem, which represents the decision problem of the evil adversary, and which is an infinite dimensional optimization problem over probability distributions. In the following, we will focus exactly on this problem. To this end, we will suppress any dependence on the fixed decision X to avoid clutter, and we will refer to the resulting problem as an uncertainty quantification problem, or primal uncertainty quantification problem. In the remainder, I would also like to assume that the disutility function G can be expressed as the pointwise maximum of several concave component functions Gi. So precisely, we will assume from now on that all negative component functions are PCC. The class of disutility functions that can be expressed in this way is actually extremely rich. So the ambiguity set script P characterizes the evil adversary's feasible set, and we will assume that it contains all probability distributions P that live on a given support set script S and that satisfy certain moment inequalities. So the support set S is described via convex constraint functions exactly like the uncertainty set in robust optimization. So I use the same notation here. We assume again that each of these constraint functions, the CLs, each of them is PCC. The moment functions in the definition of the ambiguity set require that the expected value of a vector-valued moment function H must be bounded above. And we will assume that each component of this function H is also PCC. So to develop some intuition for the uncertainty quantification problem, let us first discretize the support set S. This could conveniently be done by gridding the Z space and assuming that P is a discrete probability distribution that assigns probabilities Pk only to the grid points Zk within the set S. Now, in this case, the uncertainty quantification problem simplifies to a simple linear program in the non-negative probabilities Pk. Indeed, all expectations just reduce to probability-weighted sums, and here actually the first constraint enforces that the probabilities are normalized, so they sum up to 1, and the second constraint captures the prescribed moment inequalities. So now I would like to dualize this linear program, and to this end we assign Lagrange multipliers alpha and beta to the normalization and moment constraints. And we derived the dual linear program using the rules of standard LP duality as we learned it at school. So the dual problem has a linear inequality constraint for every discretization point in the support set. So for every k was the index of these discretization points. Now, if we successively refine the discretization grid, the number of inequalities in the dual problem will thus tend to infinity. And in the limit, the dual uncertainty quantification problem will thus have infinitely many constraints that are indexed by the infinitely many scenarios in the convex support set S. So what is remarkable about this dual uncertainty quantification problem is that it has the flavor of a robust optimization problem of the type PW. So like the primal worst we studied in the previous part of the talk. Only here, the decision variables are the Lagrange multipliers alpha and beta. The uncertain parameters correspond to Z, naturally, and the uncertainty set corresponds to the support set, the script S. Okay, so we would like now to establish strong duality between the primal and the dual uncertainty quantification problems. And so far, we've only derived dual problem heuristically, right? And these problems constitute semi-infinite programs. And of course, there is already a well-established duality theory for them. However, the strong duality conditions of semi-infinite duality theory are sometimes difficult to check. And moreover, we also want to find tractable reformulations for the two dual problems. Now, this needs additional regularity conditions in general. So in this talk, my aim is to prove strong duality together with tractability from first principles without leveraging any sophisticated results from semi-infinite duality theory. Okay. So the first idea to achieve that is to introduce a finite reduction of the primal uncertainty quantification problem. So this finite reduction reduces the original feasible set, the ambiguity set, to contain only discrete distributions with I different atoms, where I is the number of components in the piecewise concave disutility function. So the finite reduction can thus be cast as an optimization problem over the locations Zi and the probabilities lambda I of the atoms in the discrete measure. So here's a visualization of the three optimization problems of interest. The primal uncertainty quantification problem in the middle is the problem we actually want to solve. In distribution robust optimization, we actually wish to minimize the optimal value of this problem with respect to some decision variables x. Therefore, it is actually very useful to reformulate it as an equivalent minimization problem that can be merged with the minimization over x. So this minimization problems we're looking for is exactly the dual uncertainty quantification problem on the left. The finite reduction problem on the right is also very useful because it will allow us to evaluate computationally the worst case probability distributions in the ambiguity set. On the one hand, one can actually easily show that the dual and the primal uncertainty quantification problems obey a weak duality relationship. And in addition, the optimal value of the finite reduction is clearly smaller than the optimal value of the original uncertainty quantification problem because it optimized over a smaller feasible set of only discrete distributions. Our goal is now to identify conditions under which the three problems are in fact equivalent. The key idea to gain further insights into these three problems is to interpret the dual uncertainty quantification problem as an instance of the primal worst problem PW, and to interpret the finite reduction as an instance of the dual best problem DB. Okay, so let's first take a closer look at the dual uncertainty quantification problem, which I show here again. So this looks almost like an instance of the primal worst PW, but not quite. In fact, the constraint function involves a maximum of concave functions and is therefore not concave in general. However, the maximum over the I different concave disutility components here in the constraint can be removed if we split the single robust constraint up into I different robust constraints, one for each of these disutility components Gi. So now denoting the ith constraint function temporarily as Fi, we see that it is linear and therefore convex in alpha and beta. and that it is concave in Zi. And therefore, it represents a saddle function as required. However, the negative components of the disutility function, as well as the components of the moment function, h, they are PCC by assumption, so they're convex and proper and closed, and therefore they can adopt the value plus infinity as shown in the picture. And this implies that the Fi can actually adopt the value minus infinity, in which case Fi fails to be proper in alpha and beta, and therefore our results for robust optimization problems cannot be applied to this problem. Luckily, there is a simple remedy. We can introduce an auxiliary variable ui to replace the moment function h evaluated at Zi, and we can introduce an auxiliary variable ti to replace the disutility component gi evaluated at Zi. And these auxiliary variables should be interpreted as additional uncertain parameters complementing Zi. The ith robust constraint can then be reformulated as shown here, where the reformulated constraint function is bilinear in the decisions and the uncertain parameters, and where the uncertain parameters range over an augmented uncertainty set capital Ui. Now, the resulting problem is finally an instance of the primal-worst problem studied in the last part of the talk. Indeed, the bilinear constraint functions are never equal to minus infinity, and thus they are PCC in alpha and beta, so that's fine. In addition, the augmented uncertainty set is fully characterized by convex inequality constraints, and that's also what was required. In the following, I therefore refer to this optimization problem as the ambiguous primal-worst problem, APW. Okay, so we have identified the dual uncertainty quantification problem as an instance of the primal-worst problem. Now let's take a closer look at the finite reduction of the primal uncertainty quantification problem. Our goal is now to show that this finite reduction can also similarly be identified as an instance of the dual-best problem. To this end, we introduce again the auxiliary uncertain parameters ui and ti to replace h of xi and gi of zi, respectively, and we introduce again the augmented uncertainty set capital Ui for the uncertain parameters Zi, Ui, and Ti. And with these changes, the finite reduction becomes indeed an instance of the dual-best problem studied earlier. So in the following, I refer to it as the ambiguous dual-best problem, ADB. Okay, so here's a schematic of the optimization problems introduced so far. It shows that the dual uncertainty quantification problem is equivalent to the ambiguous primal-worst, which can be viewed as an instance of the primal-worst problem, so of a robust optimization problem. It also shows that the finite reduction is equivalent to the ambiguous dual-best, which can be viewed as an instance of the dual-best problem. Now, from our discussion of robust optimization problems, we know that the primal-worst and the dual-best both have convex reformulations. And the order relations between their optimal values are visualized by the blue arrows at the bottom. Now, this immediately implies that the ambiguous primal-worst and the ambiguous dual-best also have convex reformulations, which actually can be derived by simply applying our reformulation techniques that we developed before for robust optimization problems. So I don't need to go through the derivations again. Actually, I can just show you the final result. So here's the convex reformulation of the ambiguous primal-worst. And of course, I do not expect you to parse this model. I just want to show you that the dual uncertainty quantification problem is indeed equivalent to an explicit convex program that is susceptible to numerical solution. And here's the convex reformulation of the ambiguous dual-best. Okay, so again, it's a convex maximization problem, explicit. Okay, so let's return to our schematic. The primal uncertainty quantification problem in the middle constitutes actually a generalized moment problem over probability distributions. Its optimal value is squeezed by the dual uncertainty quantification problem and the finite reduction problem. The dual uncertainty quantification problem on the left is equivalent to the ambiguous primal-worst, which is a robust optimization problem. And the finite reduction problem on the right is equivalent to the ambiguous dual-best, which is a non-convex optimization problem. However, both of these ambiguous problems can be reformulated as explicit convex optimization problems that lend themselves for efficient numerical solution. So we can prove that the four problems at the bottom all share the same optimal value, either if problem ADB has a Slater point, or if problem APW has a Slater point and the support set S is bounded. So if we interpret the different problems here as nodes in a graph and the arrows as directed arcs, then we see that this resulting graph actually has a cycle. And this really means that all optimization problems have the same optimal values. And this proves strong duality for the primal and dual uncertainty quantification problems. And it also proves their tractability, so their equivalence to simple convex optimization problems. And this was derived from first principles of convex analysis, actually. Okay. So our results on distribution robust optimization and uncertainty quantification can also be generalized along several dimensions. And first, the support set and the ambiguity set can actually be characterized through generalized conic constraints. So to explain this, consider first a proper convex cone C, and recall that the cone dual to C is the set of all vectors lambda, such that lambda has a non-negative inner product with any vector x in C. This means that the angle between any vector x in C and any vector lambda in the dual cone C star is less than 90 degrees. So any proper convex cone C can be used to define generalized notions of convexity, lower semi-continuity, and properness. For example, a vector-valued function f of x is said to be C-convex with respect to a proper convex cone C if the inner product of lambda and f of x is a convex function of x for every vector lambda in the dual cone C star. Well, that's just a definition. Similarly, a vector-valued function f of x is called star C lower semi-continuous if lambda inner product of lambda and f of x is lower semi-continuous for every vector lambda in the dual cone C star. So it is therefore natural to say that f of x is CPCC, so it is proper C convex and star C lower semi-continuous if it satisfies all of these properties. Okay. And these are the kinds of functions we will study now. So now we can actually look at generalized uncertainty quantification problems, which evaluate the worst case expectation over a more general ambiguity set, script PG. This ambiguity set contains every distribution P supported on a union of convex sets, Sk. And these distributions must satisfy several generalized conic moment inequalities. And this distribution also must assign each set Sk a fixed probability Pk. So we will assume that the sets Sk are disjoint. And this implies that the probabilities Pk must sum up to 1. So these are, of course, given parameters. We also assume that each set Sk is described through generalized conic inequality, as shown here in the formula at the bottom. So the underlying constraint functions are PCC with respect to the relevant cones here. In addition, we assume that the moment function h, or each of its components, so in the component hj in the jth moment inequality, coincides with a generalized PCC function when restricted to any of the sets Sk. Okay, so it's just a simple extension of what we discussed before. Of course, makes the notation much more cumbersome. So under these conditions, we can construct generalized dual uncertainty quantification, a generalized dual uncertainty quantification problem by applying the same procedure as in the previous part of the talk. Similarly, we can construct a generalized finite reduction of the primal uncertainty quantification problem. And as before, this finite reduction evaluates the worst case expectation only with respect to certain discrete distributions in the ambiguity set. So we can then again interpret the dual uncertainty quantification problem as a primal-worst problem, which admits the explicit convex conic reformulation shown here. Similarly, we can interpret the finite reduction as a dual-best problem that admits the explicit convex conic reformulation shown here. Again, the details of the formulas do really not matter here. So the optimal values of these generalized uncertainty quantification problems and, well, all the other related problems, they're shown here again, and they're all equal if the ambiguous dual-best problem admits Slater point. So that's one possibility. Or if the ambiguous primal-worst admits a Slater point, and each of these sets Sk that form the support of the distribution P, if each of these sets is bounded. Okay. So actually these results are extremely general. They unify many classical reformulation results in distribution robust optimization. In addition, they also allow us to derive convex reformulations for certain new distribution robust optimization problems that have not yet been studied in the literature. And one such example is the uncertainty quantification problem that is shown here, which evaluates the worst case expectation of the disutility function G over an ambiguity set defined by an optimal transport distance. So this ambiguity set contains all distributions P on a given support set script S that have a distance of at most epsilon from a given nominal distribution P hat. So here we use a general optimal transport distance to measure distances between distributions. Optimal transport distances generalize the popular Wasserstein and Kantorovich distances, and intuitively the optimal transport distance between two distributions P and P prime quantifies the minimum amount of money one has to pay in order to transport the distribution P to P prime. And under the assumption that the cost of transporting a unit probability mass from a point Z to a point Z prime is given by some general distance function, lowercase d. This could be a metric on the Z space. Mathematically, the optimal transport distance is therefore defined as the minimum of the optimization problem shown at the bottom of this slide, and the decision variable Q of this problem is actually a coupling of P and P prime. Coupling is just a joint distribution of two random vectors Z and Z prime that have marginal distributions P and P prime. So the coupling Q is naturally interpreted as a transportation plan for moving probability mass. The shown optimization problem actually here aims to find the least expensive transportation plan for morphing the distribution P into P prime. So in many applications, it's natural to set the nominal distribution at the center of the ambiguity set to a discrete distribution. For example, it is often natural to identify P hat with the empirical distribution corresponding to a given set of training samples, some data that you may have about the uncertain parameters. Now, if the nominal distribution is discrete, then any transportation plan Q that morphs P into some distribution, that morphs P hat into some distribution P, any such transportation plan can be decomposed into K different pieces, one for each atom of the nominal distribution. The picture shows that the kth piece of Q is a measure supported on the Cartesian product of the support set S and the singleton set that contains only the location of the kth atom of the nominal distribution. And in the following, we denote this set by Sk. And this means that the transportation plan Q is actually supported on the union of the sets Sk. In addition, the transportation plan Q must assign to the set Sk the probability of the kth atom in the nominal distribution. Well, we denoted this by P hat K. So this is a input data for our problem. In addition, any transportation plan Q in the ambiguity set must satisfy the moment inequality shown here. So it must ensure that it uses a transportation budget of at most epsilon. It costs at most epsilon. So here actually the moment function H is identified with the transportation cost function if the second argument is equal to one of the atoms of the nominal distribution, and if it evaluates to plus infinity anywhere else. So all of these all of these things readily imply that for any distribution P in the optimal transport ambiguity set, there exists a transportation plan Q in the generalized moment ambiguity set characterized through the conditions on the previous slide. And one can therefore show that the primal optimal transport-based uncertainty quantification problem is indeed an instance of the generalized uncertainty quantification problem that I just studied in the last part of the talk. Okay, so we just reduce it to that case. And using our tools developed before, we can therefore reformulate the optimal transport-based uncertainty quantification problem directly as an explicit convex minimization problem, which allows us to efficiently solve distribution robust optimization problems, or to an explicit convex maximization problem, which allows us to efficiently compute worst case distributions. Now, both of these convex reformulations have the same optimal value as the original problem under mild standard regularity conditions. So I'd like to point out that these reformulations are new in this generality. Okay, so this brings me to the end of my talk. So in summary, we have studied first a generic convex optimization problem, and we derived an explicit representation of its dual in terms of conjugates, perspectives, and informal convolutions of the original objective and constraint functions. In the second part, we have studied robust optimization problems, which we constructed as primal worst and dual best scenario problems. We have shown that the primal worst can be convexified by dualizing the embedded subproblems, and that the dual best can be convexified by a change of variables trick. So this enabled us to derive a general primal worst equals dual best duality scheme for robust optimization problems. Then we address primal and dual uncertainty quantification problems relevant for distributionally robust optimization. We discovered that the finite reduction of the primal uncertainty quantification problem can actually be interpreted as a dual best problem, and that the dual uncertainty quantification problem can be interpreted as a primal worst problem. Now, leveraging the primal worst equals dual best duality scheme from robust optimization, we could therefore derive strong semi-infinite duality results from first principles of convex analysis, and at the same time derive explicit convex reformulations both for the primal and dual uncertainty quantification problems. We have also seen that the results on uncertainty quantification problems have made several extensions that make our duality results and convex reformulation techniques very general. As an application of these general techniques, we derived explicit convex reformulations for distribution robust optimization problems with optimal transport-based ambiguity sets. And as our results hold for piecewise concave distributivity functions, they can actually be applied in the context of single as well as two-stage distribution robust optimization, or also in the context of distribution robust chance constraint programming, just as examples. Now, as a concluding remark, I would like to highlight that the devil is often in the details, such as when lambda is 0 in a perspective function. Or other issues are that the domains of our functions may not have a point in common, or may not have a point in their relative interior, and these are things that need to be addressed to be rigorous. So I've omitted generously all of these details throughout the talk, but while working on our paper, we realized that some of these details, while important for correctness, are sometimes overlooked in the existing literature, and we see it as a main contribution of our paper to make all mathematical derivations hopefully rigorous. So if this talk caught your interest, then I would like to invite you to take a look at our working papers, especially reference 3 within the red frame. And now I thank you very much for listening in, and I look forward to answering any further questions you might have. Thank you.
Yes, thanks very much, Professor Kuhn, for this very exhaustive.
Hopefully not exhausting.
No, not to me at least. Pretty nice to start with straight up convex optimization and go all the way to distributionally robust optimization. So that was pretty amazing. Are there any questions from the audience?
Yeah, I had a question.
Yeah, Simone, go ahead.
Yeah, okay, actually two questions. One is more specific and one is more speculative. So the first one, the specific one is like, I didn't understand, for example, if Z is a random Gaussian variable. So it's like, if it's totally unbounded, that would be included in this scenario or not?
It would be included because, so, okay, in robust optimization, you use robust optimization if you argue that you do not know the distribution usually. So, but if it was a normal distribution, then the support of that variable would be just the whole space, and
so
we don't rule that out, right? I mean, our results apply in that case. So we do never assume that the support must, or the support must, or the uncertainty set must be bounded. We sometimes some duality results make that assumption, but there is always another regularity condition that also leads to strong duality, which is the existence of a Slater point, which turns out to be a much milder condition. In distribution robust optimization, it's quite natural to have unbounded supports. So we may have an ambiguity set, so a set of distributions that can live on the whole space, but we know that their mean value is 0 and their covariance matrix is bounded above, say, in a positive semi-definite sense by the identity matrix. So that's sort of you could call this a standardized moment ambiguity set, and that is captured by this framework, for example.
Okay, great. And the second one was, about this UQ formulation, the primal UQ formulation, where essentially you're looking for the supremum of some expectation of a function. So is there some way to analyze, a notion that would be in probability? Maybe you want to bound the supremum with high probability from below instead of studying the expected value. That's really more.
So just for me to be sure that I understand correctly, so we could replace the. So here we want to minimize the expected value of a function, and nature that chooses the probability distribution wants to make it as large as possible. And you say now if we replace the expectation by a probability.
No, really, so, like you want to maximize the random variable, but like maybe you want to have a lower bound that holds in high probability. Let's say your supremo of the random variable is going to be larger than something with probability 1 minus epsilon or something like that. So is that something that was studied, like the I don't know if mentioned?
Absolutely. So that's of course that's a very relevant question. And actually, so my talk didn't touch on this at all. So you're asking about the statistics, while my talk was only about the optimization aspect. So how do we reformulate these problems as something that we can efficiently solve? But the statistics is very important. So if you face a real decision-making problem, you may have to decide how do you model the uncertainty. And so I've worked quite a bit with these Wasserstein type ambiguity sets. So the ones that I discussed at the end. So I looked at the generalization of that using a general optimal transport distance. But the simplest version of this is just a ball in the space of distributions with respect to the Wasserstein metric. And so what has been done frequently is that you say, okay, we need to define the radius of this ball. And how should we choose the radius of this ball? Well, we want to make sure that sort of we're on the safe side. So ideally, we would like to ensure that the unknown true distribution is in this ball. But if we want to enforce that with probability 1, then the ball would have a radius that is probably infinitely large, and that would not be very useful. So in that case, we try to make the radius as small as possible while guaranteeing that the unknown true distribution is inside that ball with a high probability, say 1 minus beta, where beta is maybe 1% or 5%, some number that you choose. And that's actually a key benefit of these Wasserstein metrics, that there are some measured concentration results that you can use and to give you exactly such results. So you can use these Wasserstein balls as confidence regions for the unknown true distribution. Now, if the unknown true distribution is inside the ball with high probability, then the optimal value of your distribution robust optimization problem or the uncertainty quantification problem will be an upper bound on the the corresponding stochastic program, which we could solve if we knew the true distribution, with the same probability 1 minus beta. So you know that you're on the safe side with high probability 1 minus beta. It turns out if you do that, then in some sense you account for the true distribution in your decision making, and empirically this often leads to decisions that are better than if you just use a sample average approximation, or if you just try to estimate the most likely distribution that generated your data and then optimize for that one. There are other aspects to that question. So actually, if you do what I described, then if you use these measure concentration results, then still actually in practice, you will choose the radius to be much too big, and you will get over conservative decisions. And now there is actually quite a lot of literature about, how to ensure that the optimal value of a distribution robust optimization problem gives you an upper confidence bound on the optimal value of the true stochastic program with the true distribution, without necessarily enforcing that the true distribution is inside the ball. That is actually possible. So you can do that, and you can make the radius of your ambiguity set much smaller, and this results in much more reasonable decisions that still give you nice statistical guarantees, nice out of sample guarantees. Did that more or less answer the question? Maybe I digressed in the wrong direction. So please,
no, that was great. No, thank you.
Okay.
Thank you.
I think for the sake of time, maybe one more question, if there is one.
Is one in the chat, I believe?
Yeah. Abbas had a question. Without loss of generality, could we assume that the lambda i's are non-zero in the perspective of the conjugate functions in the DB problem?
Okay, we have thought about that, because as I responded as I said in response to your question, Tim, before that, we spent a lot of time making sure that we did everything correct when the lambdas are zero. And we thought about just assuming that they're strictly positive, because of course, in some limiting sense, everything should be correct if the lambda is just very small. And that intuition is correct, but I think we can construct counterexamples that you do have two constraints that are infeasible unless so both constraints involve a perspective. Say, I think you could construct problems where the constraint is feasible exactly if the lambdas are zero. So then these constraints would have a joint feasible point. But if you restrict them both to be strictly positive, I think then this would not be feasible. So I do think that this would not work in general. Then it would probably work if you assume that there is some Slater point, because then the scenario I just described couldn't happen. But this was less attractive because we also wanted to understand how the different problems relate to each other without any regularity conditions. So by that I mean just the convexity conditions, so these PCC conditions, but no assumption about Slater points or boundedness. And then once we added these technical conditions, we wanted to see, under what technical conditions can we then guarantee strong duality?
Okay, great. I think at this point we can stop the recording.